Okay, so last time we talked about the measurement. Measurement is so straightforward. We need to measure voltage of each series connected cells. So we need to measure the temperature and the current. And we came to the management. So in the management case, the battery management system, as the name suggests, the management must manage the battery, and it's going to protect, make the thermal management. It's also going to do the balancing. So the protection, we also talked about it. What I see, we talked about the protection. We talked about to manage thermal management, heating and cooling. And we came to the last part of the management. So the first management was about the protection. So it can just cut the current. The second one was the thermal management. Based on the thermal measurements, it needs to change the cooling or heating. The last one is the balancing. As we have learned, if you put many batteries in series, then we need to make sure that we balance their voltages, or we balance their charges. And in this case, we need to use the balancing, and this is also what we were discussing. Nurullah was asking that, and we were discussing about it. We can either do the passive balancing or active balancing. In the passive balancing, this energy is going to be removed as the heat. So you will have switches, and you will have resistors, and this, if you just short the battery or the cells, the series connected cells, the power is going to be removed. So this is called the passive balancing. And in this case, this resistance is going to, its value cannot be super low. It needs to have a little high value so that the current here is limited, because these resistors are usually placed on the PCB so that we don't want the PCB to get warm. In the active one, the energy is transferred between the cells. So this can be accomplished with the cells that are close by. So you cannot do it with the further away cells. And you will need extra circuits and switches between the cells so that the energy can be transferred. And the balancing can be done based on the voltage of the input voltage of the cells, final voltage, and SOC of the history. So the BMS is going to decide on those. So here, so the passive balancing or the active balancing will be done. The passive balancing is more straightforward, and active balancing gets complicated as the number of the cells increase, the series connections increase. So the next function of the battery management system is the evaluation. The most important thing is the state of charge, so that you know how much further you can drive. And the other important things are how much capacity left, the SOC, SOH, resistance. So depth of discharge is one-to-one related to more or less state of charge. And these are also important so that you know this condition of your battery. But the most important thing that you need to see is how further you can drive. So you will have some left kilometers, and just in the internal combustion engine vehicles. And moreover, the capacity. For example, if you have a 40 kilowatt hour battery when you buy the vehicle, after a couple of years, maybe your capacity can drop to 38, 36, or 35 kilowatt hours. You will also want to see the state of health of your battery, and this is going to be done by the battery management system. And the next function is going to be the external communication. So it may need to communicate with an external system, the BMS. And it's usually we can use the CAN bus system as to link the data. And so it has to communicate. And the last thing is the logging. We also want to have the parameters to be logged, and we can have the voltage, current, SOC, SOH changes, and the cell voltage limits, so it can be logged, and it can be also sent to some other devices. So the log data can also be transferred to remote location, which is called telemetry. So it needs to store some energy, and it's some data, and also it needs to send this data to remote users. So BMS, basically, it has to measure, it has to protect, it has to do the management, like the balancing and thermal management. Then it needs to tell the user the state of health and state of charge. It needs to communicate with the other parts of within the vehicle. It needs to log the data, and it needs to also send information to the other users or other devices. So BMS is a crucial equipment in a battery electric vehicle, in the cells. And I also want to, before we finish the lithium-ion batteries, I want to just show you some examples. So this example, first we will look Model S, then BMW i3, and I was trying to find some information on the Audi vehicles, but actually they are just going to give us an idea. For example, the battery pack of Tesla Model S. So this is an older photo. They have the new design now. So here is the battery. So maybe it won't be wrong that if I write here the battery, the whole thing is the battery. For example, this when I found it, it has a 85 kilowatt hour battery pack. Now the maximum battery packs are around also 100 kilowatt hours, 80, 70, 90. So this is still a good range. And it was the weight was 540 kilograms, and there were in total 7,104 lithium-ion battery cells. So what we have learned regarding lithium-ion batteries are, once you know the chemistry, you can tell the voltage, but you don't know the ampere hours, the capacity. The capacity will change depending on the size of the cell. And in this case, they use 7,000 batteries, cells, to get this 85 kilowatt hour. Then it means that they are small cells. As we discussed earlier, Tesla has the cylindrical cells, the small cylindrical cells. And here it says also there are in total 16 modules, or 14 in here and 2 in the front. Each module has 6 groups of 74 cells wired in parallel. 6 groups are then wired in series. So so it is lots of effort to do such things. 74, 6 groups, 16 modules, and you can just compare it. And they were using Panasonic cells, this 18650 cells. These are giving the diameters and the height of the cylinder. And it was more or less 20% cost of the vehicle, and more than like 25% of the weight and 25% of the vehicle cost. And here, for example, when we know the number of the cells, and if we know the ampere hour of the cells, we can calculate the kilowatt hours of the battery pack. And actually, of course, we also need to have the voltage. But when we talk about the battery charge, the capacity of a cell, we usually give ampere hour values. Maybe we can check it in the other ones. Ampere hour values. We also need to multiply it with the voltage. But since once we know the cell structure or the cell chemistry, then we know the voltage. So therefore, the capacity is usually given in ampere hours. Maybe I just write it somewhere here so we can calculate its ampere hours, 7,004 and 85 kilowatts. Okay, so another example is BMW i3. Their battery capacity increased in the last years. So when I was first teaching this course, they had really this 18.8 like years ago. The total was 22 kilowatt hours, and they had just usable part of 18.8. Then they increase it to 27.2 usable, or 33 and 27.2 usable kilowatt hours. Now they have 42.2 kilowatt hours lithium ion batteries. And with that much battery, they can travel around 300 kilometers or 350 kilometers. And in this case, they use an NCM batteries. And in the newest pack, in the 42.2 kilowatt hour pack, and I think the usable is around 39 kilowatt hours. Around, I assume. And as you see here, you are going to have 96 times 120 ampere hours multiplied by 3.7, because this is the voltage of going to be the NMC cells. This is the pack that you can see here. So maybe it is good to say here, so for battery electric vehicles, it is very common to refer to the vehicle with the amount of battery capacity. So for example, the electric machine will be the same, everything will be the same, but if you pay more, you can buy a vehicle with a higher battery capacity. So usually this is a very important factor in electric vehicles, because it is going to be directly related to the range. And as you see here, they expect to get the higher energy density, and they expect to get lower cell cost with time. And this is the all solid states. When we talk about the solid state batteries, it is the electrolyte. I don't know how to write the electrolyte. And what we know is if we can have a solid electrolyte, the system will be more compact, and it will be better in terms of the security, safety. It will be there. It won't get affected from the faults. But the problem with the solid electrolytes is the fact that they will have a high resistance, because in the electrolyte, ions should move freely. So therefore, it won't be so easy. But nowadays, the battery manufacturers work on the solid state batteries so that the system gets smaller, and we try to get the cell cost reduced. And another example is from Audi e-trons. This is a prototype, so I think this is not the vehicle that they have on the market. But anyway, they usually prepare nice pictures, so that's why I just wanted to show you. So here you see that they have 12 of 60 ampere, this one 60 ampere cells. And from that, in the next page, you see that they have 36 of it. This is what they say, 36 of it. Actually, here I can count 31, but it's fine. So they say that they have 36 of it. So these are the cells, and here is the cooling system. So the cells can be cooled, and those are the here they have also other cells. 1, 2, 3, 4, 5. Okay, 5 cells here, 31 cells here. So they have in total 36 cells. And here, this is the crash structure. So as you know, these batteries are going to be placed on the bottom of the vehicle, and it is very critical to design the system for the side crashes. From the front and back, they are quite further away, but from the side crashes, you need to design the housing nicely. And here, lower protection cover if something happens from the bottom of the vehicle, then you also need to protect them, and so on. So here you see again, they look similar. So the difference of this vehicle is they have pouch cells. It was written somewhere here, pouch cells. And here it says 36 battery modules, each 3.5 volts and 432 cells. And in this case, the total battery, so this is for a 95 kilowatt hour pack, it is around 700 kilograms. So you can also compare these values with the designs that you will end up after the project. And they use the pouch type, not the prismatic types, and they say it is easier to cool. The pouch type is easier to cool, so that's why they use the pouch type batteries. And here there are some explanations, so you can go and check the source. There are some explanations about the cooling. It says that it's normal, the cell is kept between 77 degrees and 95 degrees so that it enables fast charging and also quick that it can also deliver power if you want to have the high acceleration. And this can be only maintained if the battery vehicle is in use or it is plugged in, it has charging. Otherwise, of course, it cannot be maintained. And it says that it will use the air intake and the radiator, and so some chillers, some air conditioning to cool it down. So I think it is a nice exercise to calculate this power rating. It is going to be 36 modules, each going to have 12 pouch style cells with 60 ampere hours, and each is going to have 3.5 volts. And as a result, this is going to give you the value of watts hour for this battery pack. And if you want to understand how many of those packs or this groups of 12, each module, how many of them are connected in parallel or in series, you also need to know the voltage of the cell. For example, if the voltage of the cell is 300, it should be around 300. So VDC value is around 300 to 350 volts. Then you need to assume that 350 divided by 3.5 volts. Then we need to connect almost 10 of them in parallel, in series, or hundreds. 100 of them in the series connection. And in total, we have 433. So it means that from this 433, the packs should be, so these modules should have a higher voltage than 3.5 volts. Otherwise, we cannot reach. In the pack, so we also have some parallel connections, it means. And we need to have around 100 series connections. Then the others should be connected into parallel. So it means that in series and so on. But to be able to calculate its kilowatt hour or watt hour, you don't need it. You just need to know the capacity of one cell, voltage of one cell, and know how many of them you have in the vehicle. Okay, before we finish, I just want to show you some other news. So you can check this link. They just compare. So this is also from this Munro thing, I suppose. So Tesla Model 3, BMW i3, and Chevy Bolt battery packs are compared in terms of cost and in terms of weight. The highest capacity is Model 3, then the Chevy Bolt, then BMW i3, and you can see the difference in their costs and also in their weights and how they look. They're all placed on the bottom. That's state of art. You place the battery on the bottom. But here you can see that they have different cell types. Model S has the cylindrical, BMW i3 the prismatic, and the Chevy Bolt has this pouch type. Also, we discussed that e-tron has also used the pouch type batteries. And also this Tesla Model S, they have two versions. This is what I found recently. The one version is the Chinese manufactured one. It has MIC, made in China. And they use LFP types batteries. So lithium iron phosphate types batteries. And they are produced in China. and they have a slightly different range, 335, than the other ones that are produced in the US here, NCA batteries. And they have a slightly higher range. These NCA batteries are, I suppose, still the cylindrical type batteries. And these should be the pouch type batteries, or maybe, no, they're I think the prismatic types batteries, because it's written here, prismatic type batteries. So actually, as you can see, even you have one car and it can use different types of batteries. So one has LFP, the phosphate based, the other one is NCA. This should be the cobalt. Let's check what were those. So here the cobalt NCA, it is not here. Phosphate is here. Maybe they were here. Let's see. Lithium iron phosphate, the battery, the one that is produced in China, NMC. So here is NMC. Is what? Which one is that? I think here the nickel cosp, and anyway, we will see which one is that. So as you can see, NCA. This is NMC, sorry. It says a very long name, so I cannot see. So one of the Tesla trees have the ones that is produced in US, they have this NMC type batteries, and the ones that produce in China, they have this LFP type batteries. And as you see that NMC has a higher specific energy compared to the LFP types, but the LFP types have a longer lifetime. So here, when you see the lifetime, ideal lifetime, they actually not here, but in the other things, if you see here, they have a good lifetime, a little higher lifetime, and they have higher temperatures for the thermal runaway, and so on. So as you see, even in one vehicle, you can have different types of the batteries. And here there was also some news that the LFC, LFP times cells, they have less energy density, so the range decreased a little. But I think the LFPs are getting also better than before, and they are going to have slightly higher lifetime if you buy an LFP type battery Tesla 3. So actually this summarizes nicely what we have done. The batteries can have this different chemistries, different types, but all of them are packed on the bottom of the vehicle. We put many of them in series and parallel. If you use the prismatic cells or the pouch cells, you can use less of them because they already have a high ampere hour values. But if you use the small cylindrical cells, you need to use many of them. For example, in Tesla S, they use 7,000 of these small cells. And depending on this, but in all the systems, we need to have a BMS, battery management system, so that the voltage, currents, and the temperature of the cells are regulated, and their state of health and state of charge can be estimated. And we hope that the battery costs will decrease, because this is the biggest challenge in the battery electric vehicles, the cost of the batteries. And of course, the weight of the batteries, because you all need to carry all the weight with you. As you see that the batteries are 1/4 of the total weight of the vehicle is going to be the batteries. And we hope that the battery cost will decrease and the energy density of the batteries will increase. Okay, so we discussed about the lithium-ion batteries for a very long time now. This was the NC. I kind of mixed the batteries. Okay, so this could be also NCA, not NMC. This NMC is I3, I suppose. This NCA can be Tesla, and this can be the Tesla. When you compare it, maybe this has a better cycle life. Anyway, so each vehicle will use one of those. I kind of mix all these names, but these are different chemistries. So now we are going to have a 10 minutes break. I can just pause.